So hi guys, I'm Shubham Agrawal and today's topic is recursion. Okay, so it is one of the most important topic in GATE. Okay, so there is at least one question that comes from this area. Okay, and it is very important because one question is for sure because in all the previous year papers there is one question from this area, at least one question. Okay, so let's uh, try to understand this topic because if you have a clear understanding of this topic, then we can do any question. Okay, so let's start. Okay, so this is our today's agenda in which we are going to study about recursion, the base condition in recursion, the role of stack in recursion, direct recursion, indirect recursion. Then we will study about recursion tree. We will see some example based on recursions, like the standard example like Fibonacci series, etc. Then we will study about the applications of recursion. Then we will do some gate question based on recursion. Okay. So this is our today's agenda. Okay. So let's start. Okay. So what is recursion? Okay. So first of all, recursion is function calling itself. Okay. So if we have a function f1, okay, and that some code is written here. Okay. And then we are calling this f1 again. And again some code is written here. So here this function is again calling this function. Okay, so again this function is calling itself, and in this way this function is calling again with some different parameters. Let's suppose this n, it is called for n minus 1, and it is calling again and again, so it is recursive. Okay, so here some base condition will be mentioned. Okay, and until that base condition is satisfied, this process will go on. Okay, so let's see recursion with some example. Okay, so let me erase all this. Okay, so this is in this example, print numbers when we specify the number n equal to, let's suppose, 5. So it will print from 1 to 5. Okay, so this code. Okay, so let's see how it is printed. Okay, so okay, so in this function, this print numbers, so it is calling it again. Okay, it is calling itself again. Okay, so let me just denote a print number with Pn. Okay, so Pn of 5 is called. Okay, so 5 is not less than equal to 1. So else condition will get executed. So P of n of 4 will be called. Again, 4 is compared with this condition. So 4 is not less than equal to 1. So P of n of 3 will be called. Again, P of n of 2 will be called. And then P of n of 1 will be called. Okay, so when Pn of 1 will be called, so it will just print. It will not call this function print numbers again. So it will just print the result. So let me print the output here. So it will print 1. Then again this it will return to where it is called. Okay, so here it was called at P of Pn of 2. So then it will print 2. This print statement will get executed. Again the call will return to P of n of 3. So again 3 will be printed. Again at P of n of 4, 4 will be printed. And again to Pn of 5. So it will print 5. So it will print 1, 2, 3, 4, 5. Okay. So all this will be in the new line because I have mentioned a new line character here. So it will be something like this. 1, 2, 3, 4, 5. Okay. So this will be our output. Okay. Yeah. So let's see what are the so let me just show you that this is the base condition that we have mentioned here. Okay? So in this example, we are checking if n is less than equal to 1. So we are printing and we are not calling this function again. So this is our base condition. Okay. So let's explore base condition more. So when we are solving a bigger problem, then we try to solve it using the smaller problem recursively until some base condition is reached. Okay. Or base condition is also called a stopping condition for recursion. So if I have a problem of size n, then I will try to reduce it into n minus 1 sub problems of size less than n. Then I will try to decompose this also until some base condition is reached. So base condition is when the size of the problem is 1, then we have some solution for it. Okay. So until that problem is reduced to this, we recurse. Okay. So the base condition is very important in recursion, because if we don't take care while defining the base condition, so our program can go into infinite loop or it will cause some error. So suppose that I am calling f1 n, and in this function I am again calling f of n. So I am not taking a smaller size problem here. I am again calling it. So it will call it again and again. So it will become an infinite recursion. Okay. So there is no infinite recursion in program. You will get stack overflow error. Okay. So you will get stack overflow error because our recursion is implemented using the function stack, that is a call stack. Okay. And this when this stack gets full, so we get stack overflow error. Okay. So when the recursion is infinite, we get this stack overflow error. Okay. So let's take one example and try to understand the base condition more. Okay. So this is an example for factorial. Okay. So in this example, we have one second. So we have one function fact in 10. So we are calling fact of n. Okay. So this is factorial function. So the definition of factorial is something like this. Okay. So it is the recurrence relation for factorial, and factorial is this n into n minus 1 into n minus 2 and up to 3 into 2 into 1. So this is the definition of factorial. So it is the multiplication of all the numbers from 1 to n. Okay. So for example, 4 factorial would be 4 into 3 into 2 into 1. So it will be 12 into 2, it will be 24. Okay. So this is about factorial. Okay. And there is also a special case in this. So let me just erase it. Yeah. Okay. So there is a special case that 0 factorial is 1. Okay. And 1 factorial is also 1. Okay. So this is the special case in factorial. Okay. So in this so if we know our recurrence relation for factorial, so n factorial n into n minus 1 factorial. So we have written the function. So writing the function for that will be very easy because we just have to write the recursive relation here. So n into factor of n minus 1. Okay. And this is our base condition. That is n is less than equal to 1, then we will return 1. Okay. So the factorial for negative numbers is undefined. So we will try to give the input as a positive number only. Okay. Yeah. So let's try to find the factorial of 5. Okay. N equal to 5. Then fact of 5 will be called. Then the base condition is not satisfied here because 5 is not less than equal to 1. So we will go to the else statement, and in this it is written that n into factor of n minus 1. So factor of n minus 1 is called. So factor of 4 will be called. Again, factor of 3 will be called. Again, the factor of 2 will be called here. And then factor of 1 will be called. Okay. So factor of 1 will be called. Okay. So when factor of 1 will be called, so it will return 1. Okay. And then this 1 will be multiplied with this. So one second. So it will return 1 to factor of 2. Okay, so now it will compute the result. So it will be 2 into 1. So it will send the result 2 to factor of 3. Then 2 into 3 will happen and it will send it to factor of 4. So now 6 into 4 will happen and it will send to factor of 5. So it will be 24. Okay. And now 24 into 5 will happen and we will get our result, that is 120. Because because factorial of sorry 5 factorial is 120. Okay. So this is about the base condition. So when the base condition is reached, the recursion gets stopped. Okay, now let's see what is the role of stack in a recursion. So as we know that when we load our program in main memory, so our program looks like this. So we have the code segment, then we have a data segment, then we have if, okay, then we have stack. Okay. So in this code segment, program code will be there, and in data segment, global variable, static variable will be present. Okay, and in heap, dynamically allocated variable will be there. Okay, by using malloc or something. Okay, by using malloc alloc. Then we have stack. So if here it will be a stack will be there. So it is called function stack. Okay, or it is also called call stack. Okay, so this is about the program in main memory. So here the call stack, program stack, or a function stack. Okay, so it is used for recursion. Okay, in and each entry in this stack, okay, is called activation required. Okay, or it is also called stack frame. Okay, yeah, it is also called stack frame. So stack frame contains the local variables of the function, the input variables, input parameters, and the return address. Okay. Yeah. So these are some information that is present in the activation record. Then we have the stack pointer. So stack pointer will always point to the first entry in the stack. Okay. So it will always point to the first entry in the stack. So this function stack is used. Okay. So let's take one example. So when we are computing this factorial of 5. Okay. So we have our this is our program stack. So in this first the main function is called. Okay. Then f of 5 is called, then f of 4 is called, then f of 3 is called, then f of 2 is called, then f of 1 is called. Okay. Then when f of 1 uh, get the result, so it will return to f of 2, then f of 1 will be popped, then f of 2 will be popped, then f of 3 will be popped, f of 4 will be popped, f of 5 will be popped. Okay, so all this will return the result, and after this, this main function will be popped. So our program gets over. Okay, so in this way the function stacks works. Okay, now let's move. So in so there are two types of recursion. One is direct recursion, in which the function is calling itself, and other one is indirect recursion, in which a function is calling to another function, and this function is again calling to the function which is previously called. And okay, in this way the recursion is happening. Okay, in indirect recursion. Okay, so direct recursion is very simple. Function will call itself, and in indirect recursion, function 1 will call to function 2, and then function 2 will call function 1 again, and then function 1, and the process will repeat itself until some base condition. Here the base condition will be mentioned, so it will stop our recursion. Okay, so we will see one example of indirect recursion. So when we do some gate questions. Okay, so okay, so we will see it in the later slides. Okay, so let's take one example to compute the Fibonacci numbers. Okay, so what is Fibonacci numbers first of all? So these are the Fibonacci series. So these are the Fibonacci numbers, in which first two numbers are fixed, 0 and 1, and after that other numbers are the sum of the previous two. So we have 0 1, so it will be 1, 1 1, so it will be 2, so 1 2, so it will be 3, then 2 3, then it will be 5. So the current number will be the sum of the previous number. Okay, so the next number would be 5 plus 3, that is 8. Then 8 plus 5, that is 30. Then 13 plus 8, that is 21. 21 plus 13, 34, and so on. It can move on. Okay, so in this way we can generate the Fibonacci series. So here, as we can see, that it is a recurrence relation here. Okay, so what is that recurrence relation? So let me write it once again. So the recurrence relation is something like this. So we have f of n, and f of n is computed by the previous two values, f of n minus 1 plus f of n minus 1. Okay, and f of 0 is 0 and f of 1 is 1. Okay, so these are the base conditions. So once we know the recurrence relation, so writing the code for this is very easy. So we just have to write the method, and in which we have to just mention this base conditions. Okay, and then we just have to write this recurrence relation that is written here. Okay, so this code will generate the Fibonacci numbers. Okay, so when we give n, so when we give n equal to 5, so it will give us, so n equal to 5, so it will give 5. Okay, when we give n equal to 6, then it will give 8. When we give n equal to 7, then it will give 13. Okay, so let's take one example. Okay, so let's do it by recursion tree. Okay, so we have, suppose that we want to compute for n equal to 5. Okay, so we have fib of 5, so 5 is not uh, equal to 0, not equal to 1. Okay, so here first base condition is checked where 0 and 1 is compared. So here 5 is not equal to 0 or 1, so we will call it n 5 minus 1, which is 4. Then fib of 3. Okay, then fib of 3 will be, one second, fib of 3 will be called, then fib of 2 is called, then fib of 2 is called, then fib of 1 will be called. Okay, and here fib of 2 will be called, then fib of 1 will be called, and here fib of 1, one second, and here fib of 0 because it is n minus 2. Yeah, then we have fib of 1 here and fib of 0. Okay. And then at last we have fib of 1 and fib of 0. Okay, so this is the recursion tree for Fibonacci to compute the fifth Fibonacci number. Okay, so let me just change the color of my pen. Okay, so fib of 1 will result in 1, fib of 0 will result in 0. Similarly, here 1 will be there, 1 will be there, 0 will be there, 1 will be there, 0 will be there, and 1 will be there because they are the base conditions. Okay, and when the result again goes back to 2, then it will be 1 plus 0, so it will be 1. Then again when the result goes back to 3, then it will be 1 plus 1, so it is 2. So here it will be 1 plus 0, so it will be 1. Here also 1 plus 0, so it will be 1. Here 1 plus 1, so it will be 2. Then here 2 plus 1, so it will be 3. And at last 2 plus 3, so it will be 5. So fib of 5 will be 5. So as you can see that here this section of code, okay, and here this section of code, they are similar, means we have computed twice this thing. Okay, so so this is computed twice, so we are doing extra work here, so we can also improve the performance of this code that we have written. So for that we can use DP. Okay, so dynamic programming can be used to reduce the complexity. So currently the time complexity is 2 to the power n, and we can reduce it to n, and we can by using DP we can reduce it to n, and by using matrix exponentiation we can also reduce it to log n. Okay, so this will be the time complexity. Okay, okay. So let's move to the applications of recursion. So there are many applications of recursion, and in mostly all cases, recursion can be used because the program that can be made make using the loops. by using iterative methods. So that can be solved using recursion, and the whole problems that can be solved by recursion can also be solved by using iterative methods. Okay, so um, we can use recursion to solve tower of Hanoi, tree traversals. So see, these are some standard applications in which in order, pre-order, post-order is calculated. Then we can use it in the DFS. So we will study the tree traversal techniques, which is in order, pre-order, and post-order. In order, we first traverse left child, then root, then right. Okay. In pre-order, we first visit root, then left, then right. In post-order, we first visit left, then right, and then root. So root is visited last in this. So these are some standard traversal technique for tree. So we will study them when we study tree. Okay. Then we have DFS in graph, which is known as depth first search. Okay. So it is a graph traversing technique. So if we have a graph, something like this, okay, so we can use it to traverse it, DFS. Okay. So it generally uses recursion in which DFS code is there and some code is written, and again we call the DFS function. Okay, with some unvisited name. Okay. So yeah, so this can be recursion can be used to do that. Okay, so these are some applications of recursion. So we will study tree and graph when we study. We will study tree traversal and DSF, DFS in graph when we will study about trees and graphs. Okay, in the data structure part. Okay, so for now we will cover this tower of Hanoi application. Okay, so let me move on to tower of Hanoi. So this is Tower of Hanoi. So Tower of Hanoi, in this we have three rods. Okay, A, B, and C. So here A rod is our source rod. Okay, then B is our intermediate rod. Okay, then we have C, which is our destination rod. Okay, so in this some discs are there, and it is stacked up like this, and we have to transfer all the discs from A to C. Okay, so from this source we have to uh, means move them to destination. Okay, here. Okay, so it is a very famous mathematical puzzle. Okay, in which three rods are there, A, B, C, and n disk are there. So here I have written n equal to 3. So here three disks are used, and goal is to move all the disks from one rod to the other rod. So from rod A to rod C. Okay, so but this rule should be satisfied at each step. So we can only move one rod at a time, and we can only put the we can only move the uh, uppermost disk only of any rod. We can only move the uppermost disk. Okay, and we can't place a big disk on a smaller disk. So if I have a big disk and I have a smaller disk, then I can't put it like this. So it is a wrong way. Okay, so these are some rules. So with the help of these rules, we have to perform the operation. Okay, so let's see. So this is the C program to do that. Okay, so we have, this is for first rod, character A, character B is for say rod B, and character C for rod C. Okay, A, B, C. Okay, and n is the number of disks. N is the number of disks. Okay, so in this we try to solve it like this. Okay, so we have A, B, C. In this some disks are there. So we try to first move we try to just reduce the problem into size 2. So here problem is of size n equal to 3. So we just try to convert it to n minus 2, so n minus 1 problem size, that is for n equal to 2. We just move this to pad B, means rods B, and then we try to move this big uh, disk to rod C, and after that we move all this rod, all this disk. Okay. So in this way we can solve it. Means we can reduce our problem to n minus one. Then we can place our big disk to small disk, big disk to our final destination disk. Then we can again recurse the problem for n minus one. So in this way we can solve the problem of tower of ni. Okay. So here also in the code we first move uh, our n minus one disks to from A to B. So here it is destination, it is intermediate, and it is source. So here in n minus one, we try to move uh, n minus one disk from A to B using C. Okay. In the next step, we are doing A to C, moving the big disk to the rod C, and then we try to again solve this n minus one size problem with using A as an intermediate list and place it on C. Okay, so this is the code to do that, and when we give n equal to 3, so we will get the number of steps to do that. So let's see these steps. And also, if I have n equal to 3, so there will be 2 to the power n minus 1 steps. So 2 to the power 3 minus 1, that is 8 minus 1. So that is 7 steps. So to solve this problem for n equal to 3, we will need 7 steps to do that. For n equal to 4, it will be n equal to 4, it will be 2 to the power 4, that is 16, plus or 2 to the power 4 minus 1, that is 16 minus 1, that is 15. So we need 15 moves. Okay, so let's see it with the recursion tree. Okay, so we have TOH, Tower of Hanoi. We have 3 disks A, B, C, in which first we try to move the disk, 2 disk, upper 2 disk from A to B, and this will be the sub problems for that. And then we will move the big disk from A to C, and then we will recurse for the n minus 1 from B to C. Okay. So in this way, we can solve the problem, and you can just try the example. So it is very easy. So we first move the n minus 1 from A to B, then we place A to C, then we move from n minus 1 disk from B to C. So this will be the recursion tree, and this will be the output. Okay, so A to C, B to A, C to B, A to C, and B to A, then B to C, then A to C. Okay, so we also get the same output: A to C, B to A to B, C to B, A to C, B to A, B C, B to C, and then A to C. So this is the same output that we are getting from the recursion tree. Okay, yeah. So this is about the recursion tree for this Tower of an Eye problem. So let's visualize it. So we have 3 disks here. So we first move uh, this disk to C. Okay. Then we move our second disk to B. Then we move this again to B. Okay. Then we place A to C. Okay. Then we place this small disk to peg rod A. Then we move this to uh, rod C. Okay. Then we move this disk from rod A to rod C. So this will be our final output. And it took 7 steps. So this time complexity of this code is also 2 to the power n. Okay. For tower of n. Okay. So let's try to do some gate questions. Okay. So uh, the, the questions. So this was asked in gate 2018. So in this question, we have to compute Kelsey 4,81. Okay, and we have to print the counter value. So this question is also based on the recursion. Okay, so in this Kelsey 4,81 is called, and we have a counter variable in which is initialized with 0. Okay, when we enter in the code, so here this will be A, this will be B, and we have also a variable C. Okay. So first we increment the counter variable, so it will become 1. Then we will check whether b is equal to c the 3 or not. So here b is equal to 81, so it is not equal to 3. So we will go to the else condition. In this, calci of 4 comma b divided by 3. So 81 divided by 3, so it will be 27. Will be called. Then again counter will be incremented. Then again we will check whether 27 is equal to 3, so it is not equal. So again LC of 4 comma 9 will be called. Again counter will be increment, and we will call for LC of 4 comma 3. Okay. Now again when 4 comma 3 is called, then counter will be incremented 4, but now b is equal to 3. So it will return a cube. Okay. So it will return 4 to the power 3. Okay. And when 4 to the power 3 is written here, so in C 4 to the power 3 will be there, then 4 to the power 3 power 3. So it will be 4 to the power 9. Okay. So it will again return this. So it will again, it will be 4 to the power 9 cube. So it will be 4 to the power 27. Again, if we when it will come here, so it will be 4 to the power 81. Okay. So, but they have asked us to count the value of counter. So the counter value is 4, hence the answer would be 4. Okay. And if they have asked for the return value of this program, so it was not catch in any variable. So, but if they have asked, so it would be 4 to the power 81. Okay. So here they have asked only for counter variables, hence the answer is this. So answer is 4. Let's move to our next question, in which it was also asked in GATE 2018. So there were two questions that was asked in GATE 2018 based on recursion. Okay. So in this we have given the pseudo code, and we have to find the value of count 1024, 1024. So we have count of 1024, comma 1024. Okay. So in this, first we will compare y with 1. So y is not equal to 1 because it is 1024. Hence, we will enter in the if condition. Here also x will be compared with x. So x is 1024, which is not equal to 1. Okay. So we will execute this print statement. And in the question, they have asked us to count how many times this print statement got executed. Okay. So they have asked us that. Okay. So we will call count of 5 and 12. So it is divided by 2, comma y. So y is 1024 here. Okay. So again, it will be called for 256, comma 1024, and it will go on until count of 1, comma 1024 is there. So when 1 is not equal to 1, so this condition will false, and we will go to this condition. And in this, it is again called that 1024. So x again become 1024, and then we call y. So y now become 1023, and again the same procedure will happen. So here 2 to the power means 2 to the power 10. So we are dividing it by 2 each time. So until we get 1. Okay. So we are dividing it 10 times here. So for y equal to 1024, uh, the number of print statement that is printed is 10. Okay. So because we are calling this function 10 times. Okay. When y becomes 1023, so it again called the print function 10 times. Okay. And so on until y become 2. Okay. So it will again become print 10 times. When y become 1, so when y become 1, so this if condition is not satisfied, hence we will get out of this function. So it will not print anything. So y value is changed 103 times, and each time 10 times print statement is executed. So the answer is 210230. Okay. So A option will be our correct answer here. So this is the correct answer. Okay. So let's try to do one more question that was asked in GATE 2017 set 1. In this question, F1 is calling F2 and F2 is calling F3. So it is a question based on indirect recursion. Okay. Okay, so it is based on indirect recursion. So in this first, so we have to output the value f of fun 1 of 5. Okay, so fun 1 of 5 is called. When it is called, so first we will check whether 5 is equal to 0 or not. It is not equal to 0. So it will just print the value of 5. Then it will call fun of 2 with value 3. That is 5 minus 2. And then it will again print something. So it will print, and since it is a local variable and no changes are made, so it will again print 5 only. Okay. So we will write 5 here. Then when f2 is called, so f2 will compare 3 is with 0 0. 3 is equal to 0, so it is not equal. So it will print the value. So it will print 3. Then it will increment the value of n. So n will get incremented to 4. Okay. So here 1 of 4 will be called. And here when we print n, so it will be 4. Okay. Again 4 will be printed and 1 of 2 of 2 will be called and 4 will be printed here again. Okay. And in this 2 will be first printed and then 1 of 3 will be called. Okay. And here 3 will be printed because we have done and plus plus n. Then again 3 will be printed, then 1 of 2 will be called. So 1 of 2 not 1 of 1 will be called. So one second. Okay. So 1 of 1 will be called, and after that here 3 will be printed. When 1 of 1 will be called, so here 1 will be printed. Then 1 of 1 of 2 will be there, and then here 2 will be printed. So once again, yeah. And after that 2 will print here, and then 1 of 2 of 0 will be called, and here 2 will be printed. So when 1 2 of 0 will be called, so it will just return, it will not print anything. So here you will not get. So our output is 5 3 4 2 3 1 2. Then so first we will read from here. Okay, and then we will read upwards. Okay. Okay. So it will be 5 3 4 2 3 1 2 2 2 3 3 4 4 1. So the option which is matching to this will be our answer. So it is matching to our first option, 5 3 4 2 3 1 triple 2 double 3 double 4 5. So it is the correct answer. So our A option will be the correct answer. Let's try to do one more question. So it was asked in GATE 2016 set 2. So in this question, we have one function given in which one pointer variable and one integer variable is there, and we have this array. Okay, so we have this array in which 3 5 2 6 4 is there, and okay, and it is passed to this function f of a comma 5. Okay, so we have to find the value printed by this program. So what it will print. Okay, so we have to print the result of f of a comma 5. Okay, so when f of a comma 5 will be there, so it will compare n with, if it is less than equal to 1, so n is 5, so it will not come to this, else condition will get executed. So here we are computing max of uh, first we compare p of 0. So p of 0 will be 3 and 5. So max of 3 minus 5, so it will be minus 2. And here the result from the next function call, in which we pass p plus 1. So one second. So let me take here p only, because when we pass a comma 5, so it will be become p and n. So it is n. Okay. So p plus 1. Okay. Comma, and here n minus 1 will be there. So let me just one second. So it will be 4. Okay. So now we compute max of uh, so p of 1. So p of 0 will become, so p of 1 is this, so 5 minus 2, so it will 3. And here the result would come from p of plus 1, so it is P of 1, P of P plus 1, then P plus 1, 2, and it will become 3. Then again we will compute the max here, and the max will be 2 minus 6, so it will be minus 4. Again, P of P plus 3 will be called, and this time, and it will become 2. So max of, so here 6 minus 4, so it will become 2. And here f of P plus 4 comma 1 will be called. Here 1 is equal to less than equal to 1, so the 0 will be returned. So here 0 will be there. So maximum of 0 comma 2 is 2. So 2 will be here. Then 2 maximum of 2 comma minus 4 will be 2. So 2 will be here. Then max of 2 comma 3 will be 3. So 3 will come here. Then max of 3 comma minus 2 will be 3. So our answer would be 3. So the correct answer is 3. Okay, so in this way we can solve the question using recursion. Okay, so here the correct answer is, yeah. Let's try to, okay, so let's try to do one more question. This was asked in GATE 2016 set 1. So here we have called a count function. Okay, so here we have to return the output. So we have to execute this count of 3. Okay, so count of 3 is there, and let me write the output here. When count of 3 is called, okay, so we have a static variable, so its initial value is 1. So first we will print the value of n, so it is 3. Then we print the value of d, that is 1. Okay, so let me just print it here. Okay, so first 3 will be printed, then 1 will be printed for d, then count of 2 will be called, and d will be first incremented. Okay, and then we will call for n minus 1, so count of 2 will be called, then again d will be printed. So we will not print d here, because its value can get update in the future, so we will just mention d here, so it can get updated, so we are not writing the value here, right? Then 2 will be returned, then currently d is 2, so 2 will be printed, and then d will get incremented to 3. Then count of 1 will be called. Okay, and then the d will get printed, so we don't know the value yet. Okay. So when so when this count of 1 will be called, okay, so it will first print the value 1, then it will print the value of d, that is 3, then it will increment the value of d, and now the count is 1, so 1 is not greater than 1, so we just print the value here. So currently d is 4, so it will just print 4. And here also, when the function calls returns, so here we are printing d, so it will be 4. Here also when we return, so it will be 4. So our correct output will be 3 1 2 2 1 3 4 4 4. So our output will be 3 2 sorry 3 1 2 2 1 3 4 4 4. So this will be the correct output. Okay. Yeah, so let me run this. Yeah, so this will be the answer. So first option is matching with our answer, 3 1 2 2 1 3 4 4 4. Okay, so this is the correct answer. So in this way we can solve the gate question using recursion. So we just have to make the recursion tree, and then we can solve the question. So yeah, that's it for today's lecture.